Bam! Mr. True. In this video, we're going to be taking a look at the calculus of parametric equations, meaning we are going to analyze the slope and concavity of the curve, which is without drawing the curve, but the curve that is created by this pair of parametric equations. We're going to evaluate the slope and concavity when t is equal to 0. And we are then going to derive the slope of arc length for a curve that is described by a pair of parametric equations by starting with the arc length formula that we learned in chapter, I think it was chapter 5. Probably forgot that formula, so we'll recall that as we get going. Okay, so what tells us the slope of a curve? Okay, it might be a relation. So if I say the word function, just know I really mean to say the word relation or the curve, just basically the graph or the curve. What tells us the slope of a curve? Yeah, first derivative. So we want to look at this pair of parametric equations, which again has a close relationship with vector notation and vector formulas, but where we have a vector and component form of a vertical and horizontal component, but we're not doing vectors right now, so just get to the point. We need to find dy over dx, okay? Which means that we need to, think about how do we analyze and find first derivatives. It was the derivative with respect to x of some, well, a lot of times we use function notation, but we're taking the derivative with respect to x of y, which means that that's dy over dx. Now, of course, we have that shorthand notation of y prime, but that's not going to serve us well in this set of notes, just like it did not serve us well when we were learning implicit differentiation. We need a change of y over change of x. What's the independent variable of the equation of x, where we're tracking the horizontal movement? It has a parameter of t. So does the y equation. So does the equation of x tracks the vertical motion. So both of these parametric equations has a parameter of t. That does not match our derivative with respect to x. And we do not want to do this derivative process implicitly or with a lot of chain rule. We might have some chain rule, but it's not going to be the chain rule because we're taking a derivative with respect to x and our parameter is t. So yes, first derivative is dy over dx. Yes, we're about to find it for the curve created by this pair of parametric equations. But we need to manipulate or sort of customize this notation to show that both our vertical movement and our horizontal movement are and have a parameter, an independent variable of t. And you might figure this out naturally. Like, we want a first derivative of y. Well, the independent variable is t. So how about the derivative of y with respect to t? Can we write this? Will it make sense? Can we write this as dy over dt? Let's take the derivative of the vertical movement with respect to t. Let's take the derivative of the horizontal movement. Let's take the derivative of x with respect to t. And is this sort of expanded notation expanded to recognize that we're dealing with a pair of parametric equations where the parameter is t? Does that actually simplify to dy dx? Well, hopefully you know the answer is yes, but this is calculus notation. It's not literally the division of two fractions, but it was created to act and look like multiplication. So if we have this division of a dy dx, if we just want to make sure that this is working, and you all already kind of like quietly went, oh, okay, yeah, that makes sense. But just for someone who can't ask questions, like on YouTube, instead of showing that division of dx dt, let's bring that division of a fraction up and show it as a multiplication of the reciprocal. And oh yeah, of course, the dt's cancel out. So when you have a pair of parametric equations and you need to find the slope of that curve, and you have not eliminated the parameter, which you could actually do, eliminate the parameter and write this y in terms of x, but we want to find the slope in parametric form, you're just going to do the derivative of y with respect to t and the derivative of x with respect to t. So the derivative of y with respect to t, the derivative of 4t will be our numerator, and that, of course, is going to be 4. The derivative of the denominator, the derivative of our x function, which is t squared plus 5t plus 4. And make sure if you do show this work, and after a couple of problems you probably won't need to, but if you do show the derivative of the numerator and denominator separately, the derivative of y with respect to t and the derivative of x with respect to t, don't then start to kind of like let your brain switch into quotient rule. This is definitely not quotient rule. It's almost like sort of, it's not L'Hopital's rule, but we're taking that derivative of the numerator and denominator separately. So the derivative of t squared is 2t. The derivative of 5t is equal to 5. And so we have dy over dx. And I'm only going to write this way because I know what's coming up. We're going to bring this base out of the denominator and write this as 4 times 2t plus 5 to the negative 1. So that's our first derivative. I'm going to summarize our answer in the bottom left-hand corner because I want the first and second derivative work up here all at the same time. But let's analyze this first derivative, dy over dx, when t is equal to 0. So that's going to be, I probably could have just wrote that over there. dy over dx when t is equal to 0 is going to be equal to 4, right, times 2 times 0 plus 5 to the negative 1, which is going to be equal to 4 times 5 to the negative 1, or 4/5. Now that first derivative, dy over dx when t is equal to 0, is equal to 4/5. We're asked to analyze the slope and concavity. Is the function increasing, decreasing, constant? You know, what is this curve doing when t is equal to 0? Well, your first derivative is greater than 0, so therefore our curve is increasing when t is equal to 0. On the any kind of standardized test or free response question, make sure that you are tying your conclusion. You're making a conclusion based on your work. So maybe I should say, you know, dy over dx is greater than 0, therefore the graph is increasing when t is equal to 0. I'm sure this graph is not increasing everywhere. We only analyze the slope where t is equal to 0. The more interesting part, the more fun part, which means it's a little bit harder. The more fun part of finding and working with parametric equations is finding that concavity, discussing that second derivative. Why do I do this to myself? I hope I don't run out of time. Here's a curve that is concave up. Well, I want to talk about arc length too, and do a derivation of the formula. Why is this curve concave up? Because the slopes are increasing. At this point of tangent C, we have a tangent line, a dy over dx, which is negative. At this point of tangent C, we have a tangent line, a slope, an instantaneous rate of change at 0. And then we have a slope maybe of 1, and a slope of 2, and a slope of 3, or whatever. When you have a curve whose slopes are increasing, you have a function, and I'm just going to, for simplicity's sakes, call this f of x. So kind of go into, sort of standard rectangular language here. F of x is concave up when dy over dx is your slopes is or are increasing. And our second derivative is the blank of our first derivative. Our second derivative is the slope of the first derivative. And since you said the slopes, the first derivative is increasing, then the first derivative has to have a slope which is positive. So f is concave up where the first derivative is increasing. You really want to know that for your AP test coming up in 2.5 months. A lot of problems can be talked about and go a lot faster when you talk about concavity based on the first derivative. Or, of course, the second derivative is greater than 0. Now, right here, oh, this is coming out much better than a couple of days ago. So everybody on YouTube that watched the first video for the last couple of days, our discussion from here on out, how to find the second derivative of a curve that is described or based on a pair of parametric equations is going to be sort of the key to it is going to be, understanding why these second derivative notations are in different places, which really confused me when I first started relearning calculus. Why is the second derivative notation d squared y over sort of dx squared? And even though there's no real reason to wrap the parentheses around it, this dx squared is kind of like the whole base of dx being squared. Don't ever write that in your derivative notation, but that's how you want to think of it. Okay? The second derivative is simply the derivative of the first derivative. Okay, so promise that'll be important. Teaching at 10:30 is so much easier than 7:30. Okay, so we want to find, again, that second derivative of the curve created by this pair of parametric equations. Well, that means that we're taking the derivative with respect to x of dy over dx, just like we've been doing all year. Anybody have a problem with that? Because I do. No, it's right. I didn't make a mistake this time. No, it shouldn't be anything. No, I cut you off. What were you going to say?
The outside should be dt, and we can't.
No, it's not. Because we need, for that second derivative notation, we need a d and a d. We need a d squared. And we need a dx and a dx. We need a dx squared. This is what it needs to be. But looking at the right place. This is the derivative with respect to x. We need to take the derivative with respect to x of the first derivative. It doesn't matter, if it's y is equal to x squared plus 3, just a totally random equation I've made up. It's not related to this problem. Or y is equal to t squared plus 3 and x is equal to t. Okay, this parametric, I just pulled this rectangular equation apart into two parametric functions. I just said let x equal t basically, and boom, I got parametric equations. When you find slope, it is still change in y over change in x. Whether you're independent, whether you have a sort of standard rectangular format, a standard equation where it's y based on x, or you're tracking the vertical and horizontal movement separately. It's still change in y over change of x. We still need to take the derivative with respect to x, sort of dy over dx. But our dy over dx, our first derivative, it has a parameter of t, and we do have to work around that. And without using this expanded notation of calculus, it's going to be really hard, for me, probably impossible to understand. So dy over dx is basically kind of like a function in terms of t. Okay, let's write the function out, even though I'm going to basically kind of erase it here in a second, I think. We'll see. Dy over dx is 4 times 2t plus 5 to the negative 1 power. And Tim is on the right track. This has a t. We do need to take a derivative of this with respect to t. I need to put some notation under this d over dt. I need to put something under this that when you analyze the division of those, the division of those two calculus notations, it reduces to d over dx. So what fraction can I put down here that when I multiply by the reciprocal and have cancellation will yield a d over dx? Olivia? We need a dx over dt down here. And that is how you find a second derivative for a curve that is created by a pair of parametric equations. It is the derivative with respect to t of dy over dt divided by dx over dt. So I'm going to keep, I like the way this is written, but so I'm going to write the formula up here. We're going to take the derivative with respect to t of dy over dx and divide that by dx over dt. So we're really not doing any math with the dx dt, but we're just going to take what that function is, what that equation is, and put it in the denominator. Let me take out the dx dt and write in what it's actually equal to, wherever that was. From here, we can see, once again, just to have it in notes, we have a dy over dt, which was equal to 4, and we had a dx dt, which was our 2t plus 5. So the derivative with respect to t of 4 times 2t minus 5 to the negative 1. And in the denominator, we're just going to have 2t plus 5. So now bring the power down. Power down. Negative 1 times 4 is negative 4 times 2t plus 5 to the negative 2. And of course, we have a big formula inside the power of negative 1. So we have to finish the chain rule. The derivative of 2t plus 5 is equal to 2 over, don't take the derivative of the denominator now, that's just your dx dt, over 2t plus 5. So we have our second derivative, sort of like a d squared y over dx squared. Our second derivative is equal to, let's take this base of 2t plus 5 that has the negative 2 and bring it down to the denominator with the other base of 2t plus 5, and have negative 4 times 2 is negative 8 over 2t plus 5 to the third power. And then analyzing that second derivative, when t is equal to 0, is going to give us negative 8 over 2 times 0 plus 5 cubed, or negative 8 over 125. This second derivative is less than 0. Therefore, the parametric curve is concave down when t is equal to 0. Now, see, if I just glance at this, my y is a linear function and my x is an x squared. Honestly, I would be thinking that maybe that's a parabola opening up, but with concave down, clearly that's not the case. It would be, if the x equation was a linear function and the y equation was squared, it would be a parabola. Well, I guess maybe not definitely, but more than likely opening up. But yeah. But I'm not going to bother making a t-table or eliminating the parameter to draw that. Okay. We're only going to have a few of these in the homework, at the same level that I think you'll see on the AP test. So if you can understand that one, you should be able to get with all the homework. Arc length. Arc length is L is equal to the definite integral from a to b of the square root of 1 plus f prime of x squared dx. You learned that, and I'm sure remembered that exactly. I didn't want to insult you by asking you that formula, and you just be like, Mr. Truitt, so easy. I don't need you to tell me that. Yeah, we haven't done that in a minute. So that is arc length when f is just a basic rectangular function. What if it's parametric? What would the equation be? And this will be the same formula whether you're dealing with parametric functions or vectors coming up. I'm just going to give you a formula sheet for the vector stuff, because they keep it really basic. Okay, so let's say that x is equal to f of t. Well, this is f prime of t, f prime of x, excuse me. So since in parametric form we'd be tracking the horizontal movement with the function in terms of t, if we take the derivative with respect to t to both sides of this, we would have x prime, or dx dt, I like that better, dx dt, is equal to f prime of t, or dx is f prime of t dt. I don't do this proof all the time in derivation, so excuse me if I mess this up a little bit and have to check my notes. Same thing with y. If I do y is equal to some other function in terms of t, then by the same argument, we're going to have dy over dt is equal to g prime of t, or we have dy is equal to g prime of t dt. So in black, I have arc length based on a function that's just in rectangular format, and in blue, I have some like discussion of describing f of x as a pair of parametric equations. This is going to get converted into the definite integral from a to b of the square root of 1 plus, okay, this is the first derivative of f of x. This is like a basically a change in y over a change in x squared, or a dy over dx squared. Right? That's another notation for first derivative. Well, what's dy? It's g prime of t dt. So now we have the definite integral from a to b of the square root of 1 plus g prime of t dt, and dx was f prime of t dt squared. Well, what are the dt's going to do? Cancel out. And what notation did I forget this time, just like I forgot when I did this a few days ago? Woo! I need a dx up here. Thankfully, I caught it right away. Well, this is all in terms of rectangular format, and this is parametric form. So I need to get rid of this dx. What's dx equal to? F prime of t dt. Okay, woo, that's kind of weird. Let's see how we can get rid of that. This is not what, I know what the final formula looks like. I know, shocker. So I'm going to start doing some algebra here. Inside this square root function, we have two terms. I want to make that one term by finding a common denominator. So our denominator is f prime of t squared, right? If I square the numerator and denominator separately. So I'm going to take this 1 and multiply it by f prime of t squared, because this is 1 over 1, and this is g prime squared over f prime squared. So I'm going to find a common denominator, only without showing the work. So now we have the definite integral from a to b of the square root of, oh, they went high up, of the square root of f prime of t squared plus, I'm going to write one big fraction because I have a common denominator, plus g prime of t squared, all over our common denominator of f prime of t squared. And then remember, we took the dx out from our rectangular notation, replaced it with f prime of t dt from over here. And that looks like a plus sign or some ugly t at any least. Ooh, forgot some parentheses. Okay, well, I have a fraction inside of a square root. Can't I just take the square root of both the numerator and denominator separately? Of course I can. Right?
Yeah, sorry.
You know that, right? The square root of 9 over 4 is 3 over 2. You were just in deep thought. Okay. Okay, so, I bet the microphone liked that part. Okay, so we're going to take the square root of f prime of t squared and get, well, f prime of t. So we have the definite integral from a to b of the square root of f prime of t squared plus g prime of t squared. And then we had that f prime of t dt, but then we're taking that square root of the denominator out. And again, one more time, the square root of f prime squared is going to be f prime. I guess arguably you could say it's an absolute value sign, but that would mess up the derivative, the derivation. Yeah, let's just not even pretend like I just said that. Now, what does the two f primes do? Cancel out. So then you have arc length in parametric form, which is the definite integral. I could have just given this to you in the first place, but then you wouldn't know where it came from, and it's just because I said so, which sometimes I do that. But this derivation's fun. The arc length from a to b of the square root of f prime of t, wow, what am I writing? Squared plus g prime of t squared dt. So how are we going to use this? So that's a big long derivation for what's only going to be one example. Yay! Okay, so, but we're going to do some fancy simplification on this problem that might help you solve some complex problems when you don't have the aid of a calculator. Okay, so for one and only example of this content, we've got find the arc length. I'm not going to write this down. Find the arc length of the curve created by the parametric functions x is equal to 6t squared, y is equal to 2t cubed on the closed interval 1 to 4. Okay. What is dx dt? Did you literally make a face for doing power rule?
No, I wasn't that complicated.
It's 12t, bruh. dy over dt. I've got like 8 minutes left. I'm sorry, I'm rushing you a little bit. 2t cubed, the derivative of 2t cubed is 6t squared. And let's work through this formula that I know I'm going to have a good bout of simplifications, so I'm just going to try and rush this a little bit. Sorry. So our arc length L is going to be the definite integral. A and B are the limits, or the lower and upper limits of the closed interval. So that's going to be 1 and 4 of the square root of f prime of t. I don't remember which one of these is the vertical and horizontal movement, but it's powers and addition, so it's commutative anyway. So I'll say f of t is, I don't know, the y function. So dy dt, we have a 6t squared plus, and then our g prime of t squared, so our other derivative, 12t squared dt. Okay. Now this is a textbook problem, and it's, the answer's not that, it's a nice, easy answer. It's not one of those where, the answer's like a bazillion things and you think you've done something wrong because it gets to be too complicated. We have a definite integral from 1 to 4 of the square root. Of course, 6 squared is 36. T squared is t to the 4th. We got 12 squared, which is 144. T squared. Now we're supposed to integrate this, and this is a non-calculator question. That's a problem because you're integrating basically something, a whole bunch of stuff that's inside the power. I'm going to go back to the radical notation, but you have a whole bunch of stuff inside a power of 1/2, right? That means you have to use the chain rule if you were to integrate this. And if you're u, right, we know the integral of u to the n is n plus 1, is u to the n plus 1 divided by n plus 1. But you don't have any functions outside of the power of 1/2 or outside the square root. So in its current format, this question that looks pretty simple is, and it won't be too bad, but right now, in this format, the only way that you could analyze that definite integral is to put it in your calculator. But it's a non-calculator question, so something nice has to happen. What do these two terms have in common? A t squared. Well, 144 divided by 36, and I didn't know this, you know, I know it now because I just did this the other day, but 144 divided by 36 is 4. So you can factor out a 36 as well. So this is going to be the definite integral between 1 and 4 of the square root of 36 t squared times t squared plus 4. That's all inside the square root. I didn't say that correctly. The square root, the definite integral from 1 to 4, the square root of 36t squared times t squared plus 4 dt. And well, we can take the square root of 36 and we can take the square root of t, and now all of a sudden by doing that we'll have a function outside of the power of square root, or outside the power of 1/2. So we have a definite integral from 1 to 4 of 6t, and I'm going to integrate now, so I want to lose the radical because radicals kind of suck. So we have a 6t, and then we have the t squared plus 4 to the 1/2 power dt. And if we let u, we've done a lot of sort of moving away from full-blown u substitution, which I will continue that pattern now, but if we let u equal t squared plus 4, then du is 2t dt. Or in other words, if I want to make a u prime out here, I need to either, you know, introduce a multiple of 2 and divide by 2, or just, oh, 6 has a factor of 2. It's 3 times 2. So I'm going to bring the factor of 3 out front. And we have 3 times the definite integral from 1 to 4 of 2t times t squared plus 4 to the 1/2 power dt. This is, again, the integral of u to the n u prime or du. And the integral of u to the n u prime is u to the n plus 1. So the u prime is going to disappear. And we have 3 bracket u to the n plus 1. So t squared plus 4, add 1 to 1/2, you get 3 halves. Divide by 3 halves or multiply by 2/3. You have an upper limit of 4 and a lower limit of 1. Before I plug in the upper and lower limits and do all this math, I'm going to make my life easier by bringing out that constant of 2/3 and multiply it to the 3. So 3 times 2/3 is just going to be 2 times, now let's plug in our stuff. We have 4 squared, so we have 4 squared plus 4 to the 3/2 power minus 1 squared plus 4 to the 3/2 power. Yeah, let's go and do this. 4 squared is 16 plus 4 is 20. I'm kind of thinking about how I want to analyze this. That's going to be 20 to the 3/2 power. I think I'm going to run out of time, but just stick with me. I'm almost done. 20 to the 3/2 power minus 5 to the also 3/2 power. And I'm going to kind of keep this going as if it's multiple choice, even though if it's a free response, I think this is a great place to stop. Does 20 have a factor of 5? Yeah, it's 4 times 5. So this is going to be 2 times 4 to the 3/2 power times 5 to the 3/2 power. And I'm only looking at that because we have a 5 to the 3/2 power over here. So this 5 has a coefficient of 4 to the 3/2 power, which we're about to reduce or figure out. And this 5 has its own coefficient of 1. So we're going to bring those like terms together in a second. When you have fractional exponent, what's the top number? Power! Come on, people. What's the bottom number? If it's the top number is the power, the bottom number is the root. Thank you for talking to me, barely. What's the square root of 4? 2. What's 2 cubed? 8. So this is 8 times 5 to the 3/2 minus 1 times 5 to the 3/2. Let's add these or subtract these like, they're basically like terms even though there's no variables. Let's do 8 minus 1. Those are the coefficients. 8 minus 1 is what?
7.
Oh, you're killing me here. So we have 2 times 7. Okay, let's break this apart now. 5 to the 3 halves is equal to 5 to the 2 over 2 times 5 to the 1 over 2, right? So this is 5 times the square root of 5. So it's 8 minus 1 is 7 times 5, hold on a second, times the square root of 5. 7 times 5 is 35. 35 times 2 is 70. Square root of 5. Bang! Go to your homework. Thank you, guys. All right, A, B.